Okay, so this is a Gibbs free energy of formation. Well, when I write this, immediately, the physical chemists or the thermodynamic scientists, they like to write change, formation of Gibbs, I guess in the standard state. And depending on the academic tree, some people write this way, some people write the other way. So it's up to you. I guess here they want to prefer the heat of formation, enthalpy of formation on the right hand side. So that's the Gibbs free energy formation. The first thing to know, at constant temperature, delta G is delta H minus T delta S. So that is a definition. And then now we're just applying this one to particular formation of some compound. We just need to figure those out. And at the standard state, so that's another constraint that put it. Those are the two different kind of expanded specified version. But G is related to enthalpy and entropy combined with the temperature, and that's the one. And then changing the Gibbs free energy, what they want to know. And so let's look at the first portion, which is written here. So I guess I got that, I just plug in that number, wherever it is, I can put it in. But now I need to know the second value, delta S formation for the compound called aluminum oxide, okay, from aluminum. So aluminum, which is solid, become aluminum oxide, which is a solid. And so that's how aluminum became aluminum oxide, and that's how this is being happening this way. And they just did not provide this value to you. Just you have to figure this one out by yourself, right? So you have to write the reaction that describe this reaction, and that has something to do with delta S formation. Okay? So when you say formation means per mole basis. Okay? So here I'm in this particular problem per mole Al2O3. So that's I want to know this value. So at any rate, I need to write a chemical equation because it's a chemistry problem. So first thing is, okay, aluminum. Fine. Aluminum reacts with an oxygen. That's my aluminum oxide, is shown up here, Al2O3. So Al2O3. Yes, I have to put a solid, gas, solid. So these are the reactions. And it's not balanced, so I have to do that. And then I'm going to put another constraint. I do care, I want this one to be 1 mole. Because that's my constraint. I want the per mole basis of delta S, and I do care about just the 1 moles of Al2O3. So this is being fixed, and I have to dictate that, okay, there are 2 aluminums here, so 2. 3 oxygen atoms, so 3 over 2. I guess so that's it. That's the reaction that is relevant. So just a very simple way of writing is Al2, 3 over 2, oxygen gas reacts Al2O3 solid. And let's figure out, that's what we call formation of delta S, or even delta H and delta GF. These all related to particular for the generation formation of 1 mole of Al2O3. So that the reaction written this way is you have to spend the time in perfecting that equation. Once we have this, we are in business, right? We are in business saying that this is for that particular reaction is we just call it as a delta S. So that's, I'm going to put down constant, right? Oh, I remember delta S naught is essentially any constant times entropy for that one. Just sum it over reactant and product. I think I remember that before. For me, this is a +1. This is a -2. This is 3/2. We call it 1.5 if you want to call it. So that's the same as 3/2. And you just have to multiply those numbers and then add them together. And then you'll get delta S for that particular reaction, and we call that is a delta S naught for the formation of Al2O3. And that's the number is minus 313.1 joule per Kelvin. So here actually I'm going to do a little trick. So what I'm going to do is, let's say I want to delete this. So strictly speaking, this is an answer. Okay, you just multiply this. This is a constant we call mole. Mole times joule per mole Kelvin, so you naturally have a joule per Kelvin. That's an answer for that particular reaction written in purple here. But I can translate that information to, I written in this reaction in a way, I read in a way, this is same thing as formation, right? So, I mean, it's the same information, but now I am going to write mole. So that's the one. I guess a sort of a conceptual flow in your direction. This is for reaction as written it is, but the way this is written is for generation of 1 mole of this compound, the formation of aluminum oxide 1 mole, so that's the joule per mole. Okay. It's the same thing, but it's written in different. Am I being overcautious on this step by step? But that's the one that once you get the understanding of this, I think we'll get this. So okay, so I got this one, right? This is done and this is done. What about the temperature here? I need to calculate. So I guess I just calculate this value of delta SF. What about temperature? What's the temperature? Want to get that done? What's the temperature here? Anyone? No? Yeah?
Is it 298 Kelvin?
That's right. Why? Because?
Because it's standard temperature.
Yeah, because of the circle, right? Because of STP. So because this is already saying STP, that means 25 degrees C, and now for now is a 298 Kelvin. This is actually number-wise 298. And you can plug in everything, you will get the answer. So now we have everything. Let's go and get it done. So therefore, delta G formation of aluminum oxide, which is a delta H formation of aluminum oxide minus T, delta S formation of aluminum oxide. And this value is shown up here. Minus 16698 kilojoule per mole, and then minus 298, and then this one, right? Minus 313.1. Okay, so actually, we'll leave it there. And I need to multiply this one by 10 to the minus 3 so that I can say kilojoule per mole. Because you know this is a joule, but I want to use it as a kilojoule, so we just have to multiply by 10 to the minus 3 in front so that I can use the same value. So therefore, what you get here is minus 1576.5 5 kilojoule per mole. It's a mole of Al2O3. So that's the answer. So delta G formation here is negative, right? So this reaction is spontaneous. It happens really fast. It is fast. And if you look at here, this reaction, the aluminum, and actually I didn't read it through, but aluminum, if you have a bar of aluminum, they form the oxide thin protective layer coating as soon as they are in contact with an oxygen, which is an air. Air is abundant with an oxygen. So, you know the rust, the iron? If you have an iron, if you leave it outside, they form this red rust and just keep on growing and growing and growing. So you don't have actually no iron, everything is iron lost, iron oxide at the end. Aluminum is different. Aluminum is, once you have a bulk bar of aluminum, the surface is essentially a nice protective coating by aluminum oxide. Then the oxygen cannot permeate through the aluminum oxide. So this aluminum remains shiny for a long time, just like a stainless steel. That's why the aluminum is there. But the danger of the aluminum is the reaction is very spontaneous and the heat of enthalpy is enormous. I mean, this is like thousands of kilojoules, right? So a lot of excessive heat is coming out. So if you have a nanoparticles of aluminum metal has not been oxidized, and if you open it up, oxygen goes in, a lot of heat is liberated. Do you know what they're called? They're called bomb, right? So it is very dangerous to deal with these aluminum nanoparticles. But in the normal, our business here, aluminum has always nice protective coating so that further oxidation is prevented provided by thin layers of aluminum oxide. That's just a chemistry extra information.